explain how distillation separates the water from seawater. Now, first of all, in your syllabus, you're required to know how the drinking water supply is obtained. Okay, and this applies to the UK and many other countries like that. And it's different to obtaining drinking water by seawater, as mentioned in this question. Many countries in the Middle East, for example, obtain their water in this way because they don't get enough rainfall during the year, so they don't get enough fresh water from the rain, which ends up in rivers and streams and mountain reservoirs and various other places, which is where we get the water from in the UK for drinking. You need to know that as a separate topic. But here, this comes under the topic of separation techniques. So this is simple distillation. And here's the apparatus. You've got a flask here on the left-hand side, connected to a Liebig condenser with cold water going in and water coming out after it's circulated around the condenser. The purpose of that cold water is to cool down the condenser, okay, or to keep the condenser cold so that it can perform its function of condensing the water vapor by cooling it and turning it back from a gas into a liquid. So the salt water solution is here in the flask. When you heat it, the water boils and evaporates. You can see this vapor rising up here. And then the vapor enters the condenser. Notice the salt stays behind. Remember, the salt water is made up of solute, which is the salt dissolved in the solvent, which is the water. So the solvent rises, goes into the condenser where it gets cooled down and turns back into liquid, which then trickles into the beaker, and the water collected is called the distillate. And in this particular example, the distillate happens to be pure water, okay, or distilled water. And then obviously you wouldn't have this, so we can get rid of that. Describe how to separate the following. In each example, give a description of the procedure used and explain why this method works. So, copper powder from a mixture containing copper and zinc powders. It's not just relating to separation techniques, it's also connected to the topic of metals, specifically the reactivity of different metals. So one thing which they ask about a lot is the fact that copper does not react with dilute acids. Okay, so in this question you need to know that copper does not react with dilute acids, but zinc does. And zinc is going to form an aqueous salt solution. For example, if you react it with hydrochloric acid, it's going to form zinc chloride solution. With nitric acid, it's going to form zinc nitrate solution. Sulfuric acid, it's going to form zinc sulfate solution. Okay, but copper is not going to react with any of those dilute acids. The procedure, first of all, is going to be to take the powdered mixture in a beaker and add to it, for example, dilute hydrochloric acid. Now, it's important that you add an excess of the acid so that all of the zinc gets used up. Otherwise, you're going to get some excess zinc left over unreacted, and that's going to remain mixed with the copper. So you add excess hydrochloric acid to the mixture. How will you know when the reaction's over and all of the zinc has reacted? There's a couple of ways, but the easiest way is to remember that when acid reacts with metal, you get salt plus hydrogen. And that hydrogen is going to appear in the form of bubbles. So when the bubbles stop appearing, you know the reaction's over and all of the zinc has reacted. obviously you can heat and stir whilst you're carrying out this process. Turn all of the zinc into an aqueous salt solution, leaving the insoluble, unreacted, solid copper behind, which can then be separated by filtration. Okay, and the explanation part goes back to what I said at the beginning, which is that copper does not react with dilute acids, whereas zinc does, and turns into an aqueous salt solution, which can then be separated by filtration. The residue is going to be copper on the filter paper. If you want a pure sample of that, which they haven't asked for in the question, then you can simply wash that with distilled water and dry. Okay, so as I said, for the explanation, nitrogen from a mixture of nitrogen and oxygen. So this can be done by two ways. One is to use fractional distillation of the liquid mixture. So you need to liquefy by condensing the nitrogen and oxygen mixture, and then carrying out fractional distillation of that liquid mixture. And the explanation would be that they have different boiling points. So the boiling point of nitrogen is, I think it's about minus 196 degrees C, and oxygen minus 183 degrees C. So the nitrogen, having the lower boiling point, would boil off first and can be collected, followed by the oxygen. And the other way of doing it is to use diffusion, because the molecular mass of nitrogen, diatomic molecules N2, is 28 and oxygen is 32. Okay, there's not much of a difference there, so you're not going to get that cleaner separation, because there's, the rates of diffusion are going to be fairly close. So I would suggest that fractional distillation of the liquid mixture is a better option in this case. The explanation, as I said. Okay, finally the last part, C. Something similar to this has already been done on a previous video, so I'm not going to repeat that. This is regarding chromatography, or using chromatography to separate these two amino acids.